Alright, in this second presentation on electrochemistry, we're going to take a look at how to identify redox reactions using oxidation states, and then we'll take a look at how to balance redox reactions through a special technique called the half reaction method, and that's a really important topic in this unit. So let's begin, identifying a redox reaction. In grade 11 chemistry, you're used to seeing different types of reactions: synthesis, single replacement, double replacement, etc. In grade 12 chemistry, we look at reactions in three basic ways. We see acid-base reactions, which if you think about are a form of double replacement reaction. We see precipitation reactions, which are also a double replacement reaction. And then all other reaction types are redox reactions. Redox reactions are another name for electrochemical reactions. They're called redox because in any electrochemical reaction, reduction and oxidation have to occur together. Okay, so they have to occur together, so the reaction can be called an oxidation-reduction reaction or simply a redox reaction. When you are looking at a chemical reaction and you're wondering, is this reaction redox, the best, most reliable thing to do is to try to find a change in oxidation state from the reactants to the products. If you can find something on the left side of the equation which has a different oxidation state from its corresponding atom on the right-hand side, then you can say that this was a redox reaction. Let's see what we mean by that. Let's take a look at a few specific examples and see if we can decide if they're redox. So in this first one, we've got iron 3 plus reacting with iodide ions, forming iron 2 plus and iodine. Is this a redox reaction? Well, if we look for a change in oxidation state, we see that the iron on the left is positive 3, and the iron, the corresponding atom on the right, is only positive 2. So when iron's a reactant, it's plus 3. When it's a product, it's plus 2. That right there is all I need to know. This is a redox reaction. If you find one element, in this case iron, which changes oxidation state, this must be a redox reaction. But let's go a little bit further. What's happening to the iron 3 plus? Well, to go from plus 3 to plus 2, its oxidation state has dropped by 1. So if it dropped by 1, then my conclusion would be it's gained 1 electron. Remember that electrons are negative. If you start at plus 3 in a thermometer and you gain 1 negative, you'll go down to plus 2. So iron here has gained an electron, and that means iron 3 plus is being reduced. Okay, iron's being reduced. The iodide starts off at minus 1 as its oxidation state, and then finishes with iodine, which of course is just the element, so therefore 0 is its oxidation state. So iodide is going up in oxidation state, minus 1 up to 0, and that means it has lost an electron, and the iodide has been oxidized. Okay, losing electrons, you've been oxidized. Gaining electrons, you've been reduced. There's a common little way to remember that if you like. Leo, losing electrons, is oxidation. Leo the lion says grr, G-E-R. Okay, Leo says grr, the lion. Gaining electrons is reduction, losing electrons is oxidation. All right, try another one. Water decomposes to become hydrogen and oxygen gas. Is this redox? Well, within the water, we see hydrogens, so we know that their oxidation states are positive 1. On the right, the hydrogen there is just the element hydrogen, so 0 is its oxidation state. So since there's been a change of oxidation state for hydrogen, this must be a redox reaction. And more specifically, to go from plus 1 to 0, the water here has gained an electron. Technically the hydrogen within the water, but since the hydrogen is part of water, you'd probably end up saying water has been reduced. Now, the oxygen within water starts at -2 and finishes at 0. So the oxygen has lost 2 electrons, right? It went up in oxidation state. So in this example, water is being reduced and water is also being oxidized. It's definitely a redox reaction. Third example, whenever I see an element, like we've seen in the first two reactions, my eye immediately goes to the element. If there's an element in the reaction, like copper, 0, or silver, 0, if you see an element, then this reaction must be redox, because an element's oxidation state is 0, the copper on the left, and on the right, the copper is not 0, it's part of a compound. Now on the right, we see that's an ionic compound with 2 nitrates bonded to the copper. So that copper is an ion with a charge of +2 as an oxidation state. The silver on the left has 1 nitrate bonded to it. Nitrates are -1, so that silver is +1, and that's its charge and oxidation state. So silver is going from +1 down to 0, silver is being reduced. Copper is going from 0 to +2, it's being oxidized. Now, if all you want to know is this a redox reaction, all you need to do is just find any element that changes its oxidation state. This last example, if you looked at it with grade 11 eyes, you would probably say that looks like a double replacement reaction. And if you think about what I said at the beginning here, we said that double replacement reactions are not redox. They're either acid-base or precipitation. In this case, it's a precipitation reaction. Silver chloride is precipitating, it's not soluble. But if we look at it from an oxidation numbers perspective, the hydrogen on the left is +1, the hydrogen on the right is +1. Hydrogen does not change. Chloride on the left is -1, chloride on the right is -1. It's part of an ionic compound, it's an ion -1. Silver on the left is an ionic compound again, part of an ionic compound, so +1, and on the right it's still +1, part of an ionic compound. We could look at nitrogens and oxygens separately, or we could just say there's nitrate on the left and there's still nitrate on the right. It did not change. So nothing is changing in terms of oxidation states, so that last example is not redox. A couple more definitions that are important before we move on. An oxidizing agent and corresponding the reducing agent. Within a chemical reaction, something is getting reduced and something is getting oxidized. The thing that causes a species to become oxidized is called the oxidizing agent. Now, a simple way to identify the oxidizing agent is the idea that the oxidizing agent is what gets reduced. So within the reaction, if you know what's being reduced, that species is the oxidizing agent. The reducing agent, correspondingly, is the substance that causes something else to be reduced. And the way to identify it is that the reducing agent gets oxidized. Okay, so if you go back to the previous examples that we looked at, anything that was gaining electrons was being reduced. Therefore, that species was an oxidizing agent. The substance that was losing electrons was being oxidized, so that was a reducing agent. You might want to note that in a chemical reaction, these two things, the oxidizing and reducing agents, are always reactants. So they're always going to be on the left-hand side of an equation. You can imagine a multiple choice question asking you to identify the oxidizing agent in a reaction. You would only consider things that are reactants. Anything that's a product could not be an oxidizing or reducing agent. Apply what we've just learned. Okay, we're going to take a look at an example here. In this complicated example, can we find out what's being oxidized, what's being reduced? Can we put in oxidation numbers? Can we identify oxidizing and reducing agents? Pause the video and see if you can do that in a way similar to what we've already done. All right, did you notice that the iron starts off at +2 and the iron finishes at +3? So there's a change between the two irons. This must be a redox reaction. And as we go from +2 to +3, there's been a loss of 1 electron. So therefore, that's an oxidation process. Fe2 plus is being oxidized. Similarly, the manganese on the left is +7. The manganese on the right is +2. So the manganese has gained 5 electrons. That's a reduction process. There's no change with the oxygens. They're -2 on both sides. And there's no change with hydrogen. They're +1 on both sides. Do the same kind of thing on the reaction below, and then we'll look at oxidizing and reducing agents. So hydrogen begins with a 0. It's the element hydrogen. And on the right, +1 is part of the compound water. So hydrogen, there's been a change. It's lost 1 electron. It's been an oxidation process. Hydrogen is being oxidized. Similarly, the copper in copper oxide begins with +2 as an oxidation state, and at the end we have just the element copper, so 0. +2 to 0, we've gained 2 electrons, reduction. Remember that if your oxidation state goes up, 0 to +1, you've lost negatives, you've lost electrons. If it goes down from +2 to 0, you've gained negatives, you've gained electrons. Now, what are the oxidizing and reducing agents? Remember that the oxidizing agent was the substance that gets reduced, and the reducing agent was the substance that gets oxidized. So look at the reaction in the first one and identify the two agents. Okay, the Fe2 plus is the reducing agent since it was being oxidized, and the permanganate is the oxidizing agent since it was being reduced. In the second example, try that one. So hydrogen has been oxidized, so it's the reducing agent. Copper oxide has been reduced, so it is the oxidizing agent. All right, that pretty much ends the fundamental introductory concepts in this unit. We're going to look now at a really important skill, that's balancing redox equations. Redox equations can be very, very complicated equations. They can have 4, 5, 6 species in them, reactants and products, and then the coefficients can be really, really large and weird numbers. So balancing them by inspection, the way you would have done in grade 9, 10, or 11, just often doesn't work. So we're going to learn a method called the Half Reactions Method, which at first is going to look very complicated, but it's got a series of steps, and once you know the steps, it's actually very fast to do. So let's jump in. Redox reactions will happen in either an acid solution or a base solution, and that's important because it affects the steps that we're going to do. So I'm noting here that we're going to look at acid solutions to begin with. So we're balancing by half reaction method in an acid solution. Copy down these steps, and it's important to do them in order. You'll usually be given an equation which is a skeleton equation. It's called a skeleton equation because it'll be missing some things. Okay? It'll be missing a reactant or a product, and we're going to be fixing that as we go through the steps. We're going to split that equation into two half reactions. One of the half reactions will end up being a reduction reaction, and the other will end up being an oxidation reaction, but you don't really have to worry about that at this point. Once you've got the two half reactions, we go through a series of steps. These steps are important to do in order, and when you do them, when you apply them in balancing an equation, say them to yourself. Every time you do an example, say the steps to yourself. You'll then learn it a lot better. So the first thing we'll do is, just like in earlier grades, we'll balance by inspection all elements in the equation other than hydrogen and oxygen. So if there's any other elements besides hydrogen and oxygen, balance them the way you've always done by counting atoms and putting appropriate coefficients in. Then turn your attention to the oxygens. Balance the oxygens in a way that's going to seem weird by adding water. Okay, the reaction, you remember, is happening in an acidic solution, so there's definitely water present. And we also remember it's a skeleton equation that we started with. There was things missing. So it's quite possible that water was missing, and we're going to balance it by adding water. And that would be to fix the number of oxygens on both sides. Similarly, because the reaction was happening in an acid solution, and acids have lots of hydronium or hydrogen ions, we can fix the hydrogens, balance them, by adding H plus hydrogen ions to the appropriate side of the equation. Now we're going to do something a little weird. You've probably never considered this in balancing an equation before, but to be balanced, an equation not only has to have the same number of atoms on each side, it has to have the same total charge. Okay, in all the examples you've looked at in earlier grades, that probably just worked out to be that way. But it doesn't have to, so we're going to have to be sure that the charges are balanced on both sides of the equation by adding electrons. And we're going to represent the electrons as E negative. Okay, now if you think about it, if one side of the equation is more positive than the other side, the charge is not balanced, we'll add these negative electrons to the more positive side. And that's important. You might want to note that. Add electrons to the more positively charged side of your equation. Your goal is to make the charges on each side the same. Now the reactions are balanced in everything, atoms and charge, but you might now notice that the two half reactions have different numbers of electrons. So if necessary, multiply the two equations by some appropriate coefficients to make the numbers of electrons in each half reaction equal. The reason for that is that in the last step, we're going to recombine the equations. As we recombine the half reactions, the electrons have to cancel. The electrons will be on the left side of the equation if it is a reduction reaction. They'll be on the right side of the equation if it's an oxidation reaction. So since they're on opposite sides of the equation, and they're equal in number at this point, the electrons will cancel. However, you might also find that some water cancels, or perhaps some hydrogen ions. Anything that appears on both sides of the equation will have to cancel. All right, that probably sounds abstract and complicated. Let's take a look at a specific example. And as we do the example, it'd be good to have these steps right beside you. So here's an example of a skeleton equation. I can tell something's missing because there's oxygens on the left in the dichromate ion, but there's no oxygens at all on the right. So this can't be a complete equation. We're going to balance it using the half reaction method. So the first thing we want to do is split it into two half reactions. And that may have sounded strange, but it's now going to be pretty straightforward. There's Fe2 plus on the left, there's Fe3 plus on the right. So one half reaction is just going to say Fe2 plus becomes Fe3 plus. Now, within that reaction, we can quickly balance it, because if you go through the rest of your steps, it's said to balance the atoms other than H and O. Well, there's one Fe on both sides, that's done. It said balance the O's by adding water. There are no O's, so we're done. It said balance the H's by adding H plus. There are no H's, so we're done. It said balance charges by adding electrons. Now notice, you might even want to write it on each side. On the left, there's a total charge in the original equation of +2. On the right, there was a total charge of plus 3. So to make the charges the same on each side, I'm going to put one negative, one electron, on the more positive side, so on the right-hand side. Now each side would have a charge of plus 2, and the charges are balanced. The second half reaction is going to involve dichromate becoming chromium 3+. So dichromate, and we'll come back to that last line there, why I multiplied by 6, just hold off on that. Dichromate becomes chromium 3. The first thing we'll do, balance everything other than H and O. So go ahead and do that. So you must have noticed there was 2 chromiums on the left and only 1 on the right, so we multiply the right chromium by 2. Now balance the O's by adding water molecules. There's 7 O's on the left, there's no O's on the right, so we'll put 7 water molecules on the right. Now balance the H's with hydrogen ions. This is happening in an acid solution, so we can use hydrogen ions to balance it. There were 14 H's on the right and none on the left, so we've added 14 H's. Now let's very carefully balance the charges. Okay, I say carefully because here's where people make silly mistakes. What's the total charge right now on the left-hand side of that equation? Well, it's got a 2 negative in the dichromate. And then be careful here. The hydrogens are 1 positive, but we have 14 hydrogens. So 14 positives and 2 negatives. There's a total of positive 12 on the left. Do the same thing on the right. The waters are neutral, so we can ignore them. The chromiums are 3+. There's 2 of them, so plus 6. Now we're going to make the charges equal by adding in electrons. We put the electrons on the more positive side, so in this case on the left side. 12 and 6, the difference is 6, so we'll put 6 electrons on the left. Now, because this equation has 6 electrons, but the iron equation had only 1, we're going to multiply the iron equation by 6. We want to make the electrons the same. So if there were, think of the lowest common multiple between 1 electron and 6 electrons. The lowest common multiple would be 6. So to get 6 electrons in each equation, multiply the iron equation by 6. Now we're ready to recombine the equations. The only thing that would cancel, the only thing that's the same on both sides of the equations, are the electrons, so they're going to cancel. There's 6 on the left and 6 on the right. When I write my final equation, I'm going to put the elements and the formulas in the order that they were in the skeleton equation. So the Fe2+ first, then the dichromates, then any hydrogen ions or water. And on the product side, the Fe3+, the chromium 3+, and any hydrogen ions or water. So when we do that, we'll get an overall reaction that says 1 dichromate, and I just realized I didn't put them in the same order, but I did start with iron and dichromate, which were the things in the skeleton equation. So dichromate and 6 iron 2+, then there's 14 hydrogen ions. That's everything on the reactant side among the 2 reactions. 2 chromium 3s, 6 Fe3+, and 7 waters. That's everything that was on the product side. There's nothing the same on each side, so I know I haven't missed anything for canceling. Now you can check your answer. We can count atoms: 2 chromiums on the left, 2 chromiums on the right, 7 O's on the left, 7 O's on the right, 6 Fe's on both sides, 14 H's on both sides. We can also check the total charges. They should be the same on each side. There's 14 positives on the left, plus another 12 positives in the Fe's. 14 and 12 is 26. And then there's 2 negatives, so there's a total of positive 24 on the left. 2 times 3, there's 6 positives here on the chromiums, 6 times 3, there's 18 positives there, and the waters are neutral. 6 and 18, there's 24 positives on the right. So there's a balanced redox reaction in acid solution. Now, we just did an example that was in an acid solution, and the question would make it clear whether it was in an acid solution or not. But what if it weren't acid? What if it were in a basic solution? Well, we'd have a problem because hydrogen ion concentrations in basic solutions are really, really small. There almost is no hydrogen ion, almost, in a basic solution. On the other hand, there is a significant amount of hydroxide ions. So bases have lots of hydroxide. So what we're going to do, if the question says balance in basic solution, we would start by balancing the equation like we've done already. We would balance it as though it were in an acid solution. Okay, so it's important to note that. Start by balancing your equation as though it were in an acid solution. Then take your balanced equation, which will have hydrogen ions in it, and add enough hydroxide ions to both sides of the equation to neutralize the hydrogen ions that are there. The hydrogen ions and hydroxide ions will combine to make water molecules. Then there might be water on both sides of the equation, which has to be canceled out. Let's take a look at how to apply these two steps. We just balanced an equation in acid solution, and this is what we got. There's 14 hydrogen ions on the left. So what we're going to have to do is neutralize the 14 hydrogen ions by adding 14 hydroxide ions to both sides of the equation. There we go. Must be done to both sides, obviously, to keep the equation balanced. Now 14 H's on the left with 14 OH's on the left will make 14 waters on the left. Now there's 14 waters on the left, but there's 7 waters on the right. So if you think about it, the difference between 14 and 7 is 7 waters. And since there were more water on the left, we'll cancel 7 from both sides, and what we'll end up getting is this. Dichromate, 6 Fe2 pluses. Instead of 14 waters, we've only got 7. That's because we canceled out the 7 that were on the right. Canceled a smaller number from both sides. 2 chromium 3s, 6 Fe3 pluses, and now those 14 hydroxide ions that we added to the right-hand side as well. So there's a balanced equation in basic solution. Now it's important to note that excuse me, redox reactions happen either in an acid solution or a basic solution. They don't happen in both. So a reaction would either be a reaction in acid solution or one in basic solution, and a question would tell you which. You cannot do really what we've just done here, take a reaction which does happen in acid solution and make it happen in a basic solution. So by showing what I've done here, I've simply demonstrated the steps that you would go through to balance in basic solution. But in reality, the reaction of dichromate and iron does not happen in basic solution. It happens in acid solution. There's an important video, if you find this a little bit difficult. There's a tutorial video, and the address is on the side. It's a shortened Google web address. It'll take you to a YouTube video that goes through some examples of balancing in acid and basic solution. Try these examples here on this slide, and then if you get these wrong or if you just want some extra practice, take a look at the tutorial video. So here's an equation that happens in acid solution. Pause the video, try to go through the steps that we've learned, and get a final balanced equation in acid solution. All right, so if you've done it properly, there's the answer that you should get. 6 hydrogens on the left, meaning it was done in an acid solution. Notice the ratio: 5 moles of the oxalic acid reacts with 2 moles of permanganate. Now take one and do it in basic solution. So here is an equation that happens in basic solution. Remember to start by balancing it as though it's in an acid solution, then convert your balanced equation in acid solution to the basic solution as we did on the previous slide by adding hydroxide ions and making water. So if you've done it properly, you should have 3 cyanide ions, 2 permanganates, 1 water, and then 3 CNO minuses, 2 manganese dioxides, and 2 hydroxide ions on the right. So there's 2 good examples of balancing an acid and basic solution. And again, there's a tutorial video where I show you, if you look at the video, you'll see that I can do these balancing in a much more efficient way than I did earlier, where I showed all the different steps. Here, in the video, I go through and basically on 3, maybe 4 lines of paper, in about 2 or 3 minutes, you get the full final balanced equation. So I highly recommend that you watch the YouTube tutorial video on balancing equations.